Hello friends, so going to start reading this chapter number 2, where I stopped yesterday. I'm continuing from it. Okay, continuing it.
Train a model. At last! You framed the problem, you got the data and explored it. You sampled a training set and a test set. And you wrote a pre-processing pipeline to automatically clean up and prepare your data for machine learning algorithms. You are now ready to select and train a machine learning model.
Before starting it, what I can do, here. ठीक है. Okay, you can see that I already run the code.
Train and evaluate on the training set. The good news is that thanks to all these previous steps, things are now going to be easy. You decide to train a very basic linear regression model to get started. From Scikit-Learn model, import linear regression. linreg equal to make pipeline, linreg fit. Done. You now have a working linear regression model. You try it out on the training set, looking at the first 5 predictions and comparing them to the labels. Housing predictions equal to linreg.predict. Housing predictions round hashtag -2 equal to rounded to the nearest 100 array. Housing labels.iloscate values array. Well, it works, but not always. The first prediction is way off, while the other predictions are better. 2 are off by about 20.
1 second. So here you can see the housing prediction. You can see housing prediction. You can see. So this is a linear regression that is used here to predict housing prices. You can see that it works, but not always. The first prediction is way off by over 20, $200,000. Okay. While the other predictions are better, two are off by about 25%. You can see here. Just see here. Okay, fine. This is where you can get the data from here, and you can data from here. This is 25%. Two off for about 25%. This is 25%, 26.6%, or less than 10% is the two off. Okay, fine.
25%, and 2 are off by less than 10%.
10%.
Remember that you chose to use the RMSE as your performance measure. So you want to measure this regression model's RMSE on the whole training set using Scikit-Learn's mean squared error function with the squared argument set to false. From scikit-learn.metrics import mean squared error equal to mean squared error ln RMSE equal to mean squared RMSE equal to mean squared error. This is better than nothing, but clearly not a great score. The median housing values of most districts range between 100 and 6 example of a model underfitting the training data. When this happens, it can mean that the features do not provide enough information to make good predictions, or that the model is not powerful enough. As we saw in the previous chapter, the main ways to fix underfitting are to select a more powerful model, to feed the training algorithm with better features, or to reduce the constraints on the model. This model is not regularized, which rules out the last option. You could try to add more features, but first you want to try a more complex model to see how it does. You decide to try a decision tree regressor, as this is a fairly powerful model capable of finding complex nonlinear relationships in the data. From Scikit-Learn.tree, import decision tree.
So here we are using this decision tree regressor in this code by importing from sklearn.tree, and we are assigning it a variable called tree underscore reg, make pipeline, pre-processing, decision tree regressor, and random state is 42. As you can see, this is a random state, and now you can see here the tree reg dot fit. We are fitting it the housing with housing levels. We are fitting it the pipeline steps. You can see here, and fine.
Regressor. Tree reg equal to make pipeline, tree reg fit. Now that the model is trained, you evaluate it.
Yeah. This is the pipeline steps, column transformer, and then column transformer remainder, pipeline steps, simple emitter, strategy, median, standard scalar, standard scalar, transformer, bedrooms, and you can see here, this is the pipeline. Steps is simple immuter, and then simple immuter, then static is median, then function transformer, then function transformer whole feature names out and less than equal to fraction ratio. Name at, you can see here, to the whole code. Fine.
On the training set, housing predictions equal to tree reg.predict. Tree RMSE equal to mean squared error. Tree RMC 0. Wait, what? No error at all. Could this model really
Yeah, this is 0.0 no error at all. The housing prediction tree rec predict housing and tree RMSE, RMSE and root mean square error, housing levels and housing prediction. The housing prediction come from here and housing levels from that previous one. And we found that there is no error at all.
be absolutely perfect? Of course, it is much more likely that the model has badly overfit the data. How can you be sure? As you saw earlier, you don't want to touch the test set until you are ready to launch a model you are confident about, so you need to use part of the training set for training and part of it for model validation. Better evaluation using cross-validation. One way to evaluate the decision tree model would be to use the train test split function to split the training set into a smaller training set and a validation set. Then train your models against the smaller training set and evaluate them against the validation set. It's a bit of effort, but nothing too difficult, and it would work fairly well. A great alternative is to use Scikit-Learn's k-fold cross-validation feature. The following code randomly splits the training set into 10 non-overlapping subsets called folds. Then it trains and evaluates the decision tree model 10 times, picking a different fold for evaluation every time and using the other 9 folds for training. The result is an array containing the 10 evaluation scores from Scikit-Learn.model selection.
So battery evaluation using cross validation, you can see here. We have used tree RMSEs and cross value score, as you can see here. Okay, fine.
Import cross-val score.
Cross
Tree
value.
RMSE is equal to cross-val score. Scikit-Learn's cross-validation features expect a utility function rather than a cost function. So the scoring function is actually the opposite of the RMSE. It's a negative value, so you need to switch the sign of the output to get the RMSE scores. Let's look at the results. PD series.describe count 10, 60, 6, 800, and 68. 6800, 642, 5 minutes. Mean STD 2000 and 60T 2000. 649.49 300, 38.0, 70 50%, and 1.94 75%. Now the decision tree doesn't look as good as it did earlier. Now that cross-validation allows you to get not only an estimate of the performance of your model, but also a measure of how precise this estimate is. The decision tree has an RMSE of about 66,868, with a standard deviation of about 2,061. You would not have this information if you just used one validation set. But cross-validation comes at the cost of training the model several times, so it is not always feasible. If you compute the same metric for the linear regression model, you will find that the mean RMSE is 69,858, and the standard deviation is 4,182. But the difference is minimal due to severe overfitting. We know there's an overfitting problem because the training error is low while the validation error is high. Let's try one last
So
model.
here, this line is very important. We know that our fitting column. Why the our fitting is column? Because the training error is low, actually zero. While the validation error is high. So we can see here, the validation error is high.
Now, the random forest regressor. As you will see in Chapter 7, random forests work by training many decision trees on random subsets of the features, then averaging out their predictions. Such models composed of many other models are called ensembles. They are capable of boosting the performance of the underlying model. The code is much the same as earlier. From Scikit-Learn.ensemble import random forest regressor. Forest reg equal to make pipeline, preprocessing. Forest RMSE is equal to cross-val score, scoring equal to neg root.
We have to change the sign, the minus, the cross value, and putting the scoring. Neg root means square error and CV10.
Mean squared error, CV equal toten. Let's look at the scores. PD series. Let's look at the scores. Describe 1047,000 and 19.95, 612821, 5T458, 11123, 4064, 4060
Nice.
7596325. Max. However, if you train a random forest and measure the RMSE on the training set, you will find roughly 17,474. That's much lower, meaning that there's still quite a lot of overfitting going on. So, to simplify the model, constrain it, or get a lot more training data. Before you dive much deeper into random forests, however, you should try out many other models from various categories of machine learning algorithms, without spending too much time tweaking the hyperparameters. The goal is to shortlist a few promising models. Fine-tune your model. Let's assume that you now have a short list of promising models. You now need to fine-tune them. Let's look at a few ways you can do that. Grid search. One option would be to fiddle with the hyperparameters manually until you find a great combination of hyperparameter values. This would be very tedious work, and you may not have time to explore many combinations. Instead, you can use Scikit-Learn's Grid Search CV class to search for you. All you need to do is tell it which hyperparameters you want it to experiment with, and what values to try out, and it will use cross-validation to evaluate all the possible combinations of hyperparameter values. For example, the following code searches for the best combination of hyperparameter values for the random forest regressor. From Scikit-Learn.model selection, import grid search CV. Full pipeline equal to pipeline. Random forest max features. Preprocessing GON clusters.
Nice.
Random forest max features. Grid search equal to grid search CV grid search fit. Notice that you can refer to any hyperparameter of any estimator in a pipeline, even if this estimator is nested deep inside several pipelines and column transformers. For example, when Scikit-Learn sees preprocessing GON clusters, it splits this string at the double underscores. Then it looks for an estimator named preprocessing in the pipeline and finds the preprocessing column transformer. Next, it looks for a transformer named GO inside this column transformer and finds the cluster similarity transformer we used on the latitude and longitude attributes. Then it finds this transformer's n clusters hyperparameter. Similarly, random forest max features refers to the max features hyperparameter of the estimator named random forest, which is of course the random forest model.
Well, yeah.
Wrapping preprocessing steps in a Scikit-Learn pipeline allows you to tune the preprocessing hyperparameters along with the model hyperparameters. This is a good thing since they often interact. For example, perhaps increasing n clusters requires increasing max features as well. If fitting the pipeline transformers is computationally expensive, you can set the pipeline's memory hyperparameter to the path of a caching directory. When you first fit the pipeline, Scikit-Learn will save the fitted transformers to this directory. If you then fit the pipeline again with the same hyperparameters, Scikit-Learn will just load the cache transformers. There are two dictionaries in this param grid, so grid search CV will first evaluate all 3 times 3 equal to 9 combinations of n clusters and max features hyperparameter values specified in the first dict. Then it will try all 2 times 3 equal to 6 combinations of hyperparameter values in the second dict. So in total, the grid.
So you can see there are two dictionary in this parameter grid. So grid search CV will first evaluate all the combination. Here 3 cross 3. That's 9 combinations of n clusters and uh, max features hyperparameter values specified in the first dict. Then it will try 2 cross 3. 2 cross 3 6 combination of hyperparameters value in the second dictionary. You can see in the second dictionary as well. Nice. So in the total grid research will explore 9 plus 6, 15 combinations. Okay.
Search will explore 9 plus 6 equal to 15
15
combinations of hyperparameter values, and it will train the pipeline 3 times per combination, since we are using threefold cross-validation. This means there will be a grand total of 15 times 3 equal to 45 rounds of training. It may take a while, but when it is done, you can get the best combination of parameters like this. Grid search, .best params. In this example, the best model is obtained by setting n clusters to 15 and setting max features to 8.cv arrays equal to PD data frame. Is the maximum value that was evaluated for n clusters. You should probably try searching again with higher values. The score may continue to improve. You can access the best estimator using grid search best estimator. If grid search CV is initialized with refit true, then once it finds the best estimator using cross-validation, it retrains it on the whole training set. This is usually a good idea, since feeding it more data will likely improve its performance. The evaluation scores are available using grid search.cv results. This is a dictionary, but if you wrap it in a data frame, you get a nice list of all the test scores for each combination of hyperparameters and for each cross-validation split, as well as the mean test score across all splits. CV res sort values. Hashtag change column names to fit on this page, and show RMSE equal to score CV res head. Hashtag note, the first column is the row ID. The mean test RMSE score for the best model is 44,042, which is better than the score you got earlier using the default hyperparameter values. Congratulations, you have successfully fine-tuned your best model. Randomized search. The grid search approach is fine when you are exploring relatively few combinations, like in the previous example. But randomized search CV is often preferable, especially when the hyperparameter search space is large. This class can be used in much the same way as the grid search CV class, but instead of trying out all possible combinations, it evaluates a fixed number of combinations, selecting a random value for each hyperparameter at every iteration. This may sound surprising, but this approach has several benefits. If some of your hyperparameters are continuous, and you let randomized search run for, say, 1,000 iterations, Then it will explore
Okay.
1,000 different values for each of
For
these
each of these
hyperparameters,
hyperparameters.
whereas grid search would only explore the few values you listed for each one. Explore the few values you listed, but you don't know it yet. If it has 10 possible values and you add it to your grid search, then training will take 10 times longer. But if you add it to a random search, it will not make any difference. If there are 6 hyperparameters to explore, each with 10 possible values, then grid search offers no other choice than training the model a million times, whereas random search can always run for any number of iterations you choose. For each hyperparameter, you must provide either a list of possible values or a probability distribution. From Scikit-Learn model selection, import randomized search CV. From scipy.stats, import randint. Param distribs equal to R&D search equal to randomized search CV. Full pipe.
So here you can see the code that from Scikit-Learn model selection, we imported this randomized search CV, and from scipy.stats we imported the randint, random integer. Okay, now the parameter distribution, you can see the preprocessing geo and clusters. The random entity is given from low 83 and high 50. And for next features, we give the random int low to high 20. Now the random search is equal to randomized search CV full line. You can see this.
Pipeline. Param distributions param distribs. And iter equal toten. CV equal to 3. Scoring equal to negroot mean squared error. R&D search fit.
Okay, the scoring is neg root mean square error. And random state is 42. You can see this. The random search dot fit.
Scikit-Learn also has having random search CV and having grid search CV hyperparameter search classes. Their goal is to use the computational resources more efficiently, either to train faster or to explore a larger hyperparameter space. Here's how they work. In the first round, many hyperparameter combinations are generated using either the grid R&D search fit. Scikit-Learn also has having random search CV and having grid search CV hyperparameter search classes. Their goal is to use the computational resources more efficiently, either to train faster or to explore a larger hyperparameter space. Here's how they work. In the first round, many hyperparameter combinations are generated using either the grid approach or the random approach. These candidates are then used to train models that are evaluated using cross-validation, as usual. However, training uses limited resources, which speeds up this first round considerably. By default, limited resources means that the models are trained on a small part of the training set. However, other limitations are possible, such as reducing the number of training iterations if the model has a hyperparameter to set it. Once every candidate has been evaluated, only the best ones go on to the second round, where they are allowed more resources to compete. After several rounds, the final candidates are evaluated using full resources. This may save you some time tuning hyperparameters. Ensemble methods. Another way to fine-tune your system is to try to combine the models that perform best. The group will often perform better than the best individual model, just like random forests perform better than the individual decision trees they rely on, especially if the individual models make very different types of errors. For example, you could train and fine-tune a k-nearest neighbors model, then create an ensemble model that just predicts the mean of the random forest prediction and that model's prediction. We will cover this topic in more detail in Chapter 7, analyzing the best models and their errors. You will often gain good insights on the problem by inspecting the best models. For example, the random forest regressor can indicate the relative importance of each attribute for making accurate predictions. Final model equal to R&D search best estimator. Hashtag includes preprocessing. Feature importances equal to final model. Feature importances. Feature importances round. Array. 0.01. Let's sort these importance scores in descending order and display them next to their corresponding attribute names. Sorted. Zip. Feature importances. Final model.
Here you can see feature importance dot down to array 0.07, 0.05, 0.05. This is you can see.
These importance scores in descending order and display them next to their corresponding attribute names. Sorted. Zip. Feature importances. Final model. Get feature names out. Reverse equal to true. With this information, you may want to try dropping some of the less useful features. The Scikit-Learn.feature selection. Select from model transformer can automatically drop the least useful features for you. When you fit it, it trains a model, looks at its feed to importances attribute, and selects the most useful features. Then when you call transform, it drops the other features. You should also look at the specific errors that your system makes. Then try to understand why it makes them and what could fix the problem. Adding extra features or getting rid of uninformative ones, cleaning up outliers, etc. Now is also a good time to ensure that your model not only works well on average, but also on all categories of districts, whether they're rural or urban, rich or poor, northern or southern, minority or not, etc. Creating subsets of your validation set for each category takes a bit of work, but it's important. If your model performs poorly on a whole category of districts, then it should probably not be deployed until the issue is solved, or at least it should not be used to make predictions for that category, as it may do more harm than good. Evaluate your system on the test set. After tweaking your models for a while, you eventually have a system that performs sufficiently well. You are ready to evaluate the final model on the test set. There is nothing special about this process. Just get the predictors and the labels from your test set, and run your final model to transform the data and make predictions, then evaluate these predictions. X test equal to strat test set drop. Y test equal to strat test set. Copy. Final predictions, final model.predict. Final RMSE equal to mean squared error print hashtag prints 41,400 and 24.40026462184. In some cases, such a point estimate of the generalization error will not be quite enough to convince you to launch. What if it is just 0.1% better than the model currently in production? You might want to have an idea of how precise this estimate is. For this, you can compute a 95% confidence interval for the generalization error using scipy.stats. Interval. You get a fairly large interval from 39,200, 275. And your previous point estimate of 41,424 is roughly in the middle of it. From performance for this, you can compute a 95% confidence interval for the generalization error using scipy.stats. Interval. You get a fairly large
interval from 39,275 to 43,467. This is a fairly large interval. You can compute 95% confidence interval for generalization error using sci.stats.t interval, and you can get a fairly large interval from this. And you, in the previous point estimate
interval from 39,200, 275. And your previous point estimate of 41,424 is roughly in the middle of it. From performance for that mean, if you did a lot of hyperparameter tuning, that's because your system ends up fine-tuned to perform well on the validation data, and will likely not perform as well on unknown datasets. That's not the case in this example since the test RMSE is lower than the validation RMSE. But when it happens, you must resist the temptation to tweak the hyperparameters to make the numbers look good on the test set. The improvements would be unlikely to generalize to new data. Now comes the project pre-launch phase. You need to present your solution, document everything, and create nice presentations with clear visualizations and easy-to-remember statements.
Nice.
In this California housing example, the final performance of the system is not much better than the experts' price estimates, which were often off by 30%, but it may still be a good idea to launch it, especially if this frees up some time for the experts so they can work on more interesting and productive tasks. Launch, monitor, and maintain your system. Perfect, you got approval to launch. You now need to get your solution ready for production. Then you can deploy your model to your production environment. The most basic way to do this is just to save the best model you trained, transfer the file to your production environment, and load it. To save the model, you can use the joblib library like this. Import joblib. Joblib dump. It's often a good idea to save every model you experiment with so that you can come back easily to any model you want. You may also save the cross-validation scores and perhaps the actual predictions on the validation set. This will allow you to easily compare scores across model types and compare the types of errors they make. Once your model is transferred to production, you can load it and use it. For this, you must first import any custom classes and functions the model relies on, then load the model using joblib and use it to make predictions. Import joblib. Import kmeans, base estimator, transformer mixin, RBF kernel, etc., def column ratio, def ratio name, class, cluster similarity, final model reloaded jobload, my California housing model.pkl. New data equal to hashtags to make predictions for predictions equal to final model reloaded predict.
So here you can see the code that function is defined here. The column ratio x, return x, that full list will be returned containing 0 and 1. I'm feeling it right. Nice.
For example, perhaps the model will be used within a website. The user will type in some data about a new district and click the Estimate Price button. Query containing the data to the web server, which will forward it to your web application. And finally, your code will simply call the model's predict method. Alternatively, you can wrap the model within a dedicated web service that your web application can query through a REST API. This makes it easier to upgrade your model to new versions without interrupting the main application. It also simplifies scaling, since you can start as many web services as needed and load balance the requests coming from your web application across these web services. Moreover, it allows your web application to use any programming language, not just Python. Figure 2-20. A model deployed as a web service and used by a web application. Another popular strategy is to deploy your model to the cloud, for example on Google's Vertex AI. Just save your model using joblib and upload it to Google Cloud Storage. Then head over to Vertex AI and create a new model version, pointing it to the GCS file. That's it. This gives you a simple web service that takes care of load balancing and scaling for you. It takes JSON requests containing the input data and returns JSON responses containing the predictions. You can then use this web service in your website. As you will see in Chapter 19, deploying TensorFlow models on Vertex AI is not much different from deploying Scikit-Learn models. But deployment is not the end of the story. You also need to write monitoring code to check your system's live performance at regular intervals and trigger alerts when it drops. It may drop very quickly, for example, if a component breaks in your infrastructure, but be aware that it could also decay very slowly, which can easily go unnoticed for a long time. This is quite common because of model rot. If the model was trained with last year's data, it may not be adapted to today's data, so you need to monitor your model's live performance. But how do you do that? Well, it depends. In some cases, the model's performance can be inferred from downstream metrics. For example, if your model is part of a recommender system, and it suggests products that the users may be interested in, then it's easy to monitor the number of recommended products sold each day. If this number drops, then the prime suspect is the model. This may be because the data pipeline is broken, or perhaps the model needs to be retrained on fresh data. However, you may also need human analysis to assess the model's performance. For example, suppose you trained an image classification model to detect various product defects on a production line. How can you get an alert if the model's performance drops before thousands of defective products get shipped to your clients? One solution is to send to human raters a sample of all the pictures that the model classified. Depending on the task, the raters may need to be experts, or they could be non-specialists, such as workers on a crowdsourcing platform. In some applications, they could even be the users themselves, responding, for example, via surveys or repurposed CAPTCHAs. Either way, you need to put in place a monitoring system, as well as all the relevant processes to define what to do in case of failures and how to prepare for them.
Yeah.
Unfortunately, this can be a lot of work. In fact, it is often much more work than building and training a model. If the data keeps evolving, you will need to update your datasets and retrain your model regularly. You should probably automate the whole process as much as possible. Here are a few things you can automate. Collect fresh data regularly and label it. Write a script to train the model and fine-tune the hyperparameters automatically. This script could run automatically, for example, every day or every week, depending on your needs. Write another script that will evaluate both the new model and the previous model on the updated test set, and deploy the model to production if the performance has not decreased. The script should probably test the performance of your model on various subsets of the test set, such as poor or rich districts, rural or urban districts, etc. You should also make sure you evaluate the model's input data quality. Sometimes performance will degrade slightly because of a poor quality signal, but it may take a while before your system's performance degrades enough to trigger an alert. If you monitor your model's inputs, you may catch this earlier. For example, you could trigger an alert if more and more inputs are missing a feature, or the mean or standard deviation drifts too far from the training set, or a categorical feature starts containing new categories. Finally, make sure you keep backups of every model you create and have the process and tools in place to roll back to a previous model quickly, in case the new model starts failing badly for some reason.
Nice. This is very
Having
good.
backups also makes it possible to easily compare new models with previous ones.
Yeah.
Similarly, you should keep backups of every version of your dataset so that you can roll back to a previous dataset if the new one ever gets corrupted. Having backups of your datasets also allows you to evaluate any model against any previous dataset. As you can see, machine learning involves quite a lot of infrastructure. Chapter 19 discusses some aspects of this, but it's a very broad topic called ML operations, which deserves its own book. So don't be surprised if your first ML project takes a lot of effort and time to build and deploy to production. Fortunately, once all the infrastructure is in place, going from idea to production will be much faster. Try it out. Hopefully this chapter gave you a good idea of what a machine learning project looks like, as well as showing you some of the tools you can use to train a great system. As you can see, much of the work is in the data preparation step, building monitoring tools, setting up human evaluation pipelines, and automating regular model training. The machine learning algorithms are important, of course, but it is probably preferable to be comfortable with the overall process and know 3 or 4 algorithms well rather than to spend all your time exploring advanced algorithms. So, if you have not already done so, now is a good time to pick up a laptop, select a dataset that you are interested in, and try to go through the whole process from A to Z. A good place to start is on a competition website such as Kaggle. You will have a dataset to play with, a clear goal, and people to share the experience with. Have fun. Exercises. The following exercises.
So going to start practicing exercises with a single solution and also implementing by myself also. Okay, going to start very soon. Okay, continuing it, the exercises. So starting from the first
Are
question.
based on this chapter's housing dataset. 1. Try support vector machine regressor with various hyperparameters such as kernel equal to linear or kernel equal to RBF. Note that support vector machines don't scale well to large datasets, so you should probably train your model on just the first 5,000 instances of the training set and use only 3-fold cross-validation, or else it will take hours. Don't worry about what the hyperparameters mean for now, we'll discuss them in Chapter 5. How does the best SVR predictor perform?
Okay. Let's try it out. So here you have seen, yeah, you are seeing that this code from sklearn to model selection import grid search CV as is given here. Uh, One second, this is not okay. So it is given that you have to use this sklearn.svm svr. So we have to import svr from the sklearn.svm. Okay, and for the grid search, we are using this library, this grid search CV. Param grid, you can see CVR kernel and all the values are included. So linear, you can see it. And RBF is also included as given here. Linear is included, kernel equal to linear or kernel equal to RBF. Both are included here. And SVRC is included. This is included here. And SVR gamma, you can see here. SVR gamma. Okay, SVRC is there. SVR gamma is there. And 0.01 and 0.03, 0.1 is there. Okay. And SVR pipeline, you can see the pipeline pre-processing, pre-processing SVR and SVR that's using. And research CV, you can see this, and research sheet, you can see this. Okay, fine. And this is the final results you can see here. Okay, that's cool. So pre-processing is that by using the pipeline because it is given that you have to use that what is hyperparameter I use and when last doesn't so just the first 5,000 instances of the training set there is only threefold you're using threefold you CV equal to 3 SER so you threefold and research and that's good and SER grid search RMSE grid search best models following score this is the score that's much worse than random forest regressor but to be fair we trained the model on much less data let's check the best parameter found you can find a linear kernel seems better than RBF kernel you can see here the linear kernel data and RBF kernel okay fine this is the fine so linear kernel seems better than RBF kernel notice that the value of C is the maximum tested value when this happens, you definitely want to solve the grid search again with higher value of C, removing the smallest value because it is likely the higher value of C will be better. Okay, so try replacing.
2. Try replacing the grid search CV with a randomized search CV.
So just trying to replacing grid search CV with randomized CV. Okay, here you can see SVR CV, SVR gamma. You can see here linear RBF 20, 25. Okay, you can. Here is perfect. You can randomize search CV, but grid search CV. It's really cool. Okay, next.
3. Try adding a select from model transformer in the preparation pipeline to select only the most important attributes. 4. Try creating a custom transformer that trains a k-nearest neighbors regressor.
So you can see all the questions and the respective answer are given in this notebook. You can see and check out each and every answer. So I'm going to wrap up this session
In its
now.
fit method and outputs the model's predict.
Okay, fine.
Lastly, implement the get feature names out method.
Okay, I will
Solution.
implement it after having the summary of this chapter now. Going to summarize this chapter number 2. Okay, make bullet points, deep dive, and select pages. Not pages, select chapters. Okay, selecting the chapter number 2. Okay, I will summarize all the. Let's try it out. Continue. Get summary. Okay, turning into summary. It will take some time. So I will what I will do. Okay, starting it from here.
Projects. End-to-end machine learning projects. 1. The machine learning project lifecycle. Project scope and definition. Every machine learning project begins with a clear business objective. In the fictitious scenario of the Machine Learning Housing Corporation, the goal is to predict median housing prices based on census data. This objective determines the problem framing, in this case, a multiple regression task using supervised batch learning. and the selection of performance metrics such as RMSE or ME to evaluate model accuracy. Data acquisition and initial exploration. Using real-world data like the StatLib California housing prices dataset is essential for skill acquisition. Initial exploration involves understanding data structure through methods like head, info, and describe. Visualizing data with histograms and scatterplots helps identify geographical patterns, correlations, and potential data quirks, such as the capped values in median house value. Data preprocessing pipelines. Preparing data is a critical iterative stage that involves cleaning missing values through imputation and applying feature transformations. Using pipelinean column transformer from Scikit-Learn ensures that transformations are reproducible and modular. Standardizing features or applying transformations like logarithms or RBF kernels helps mitigate issues like skewed distributions and differing input scales. 2. Model selection and refinement. Training and evaluation. Once data is preprocessed, one begins with a baseline linear regression model. If the initial performance is insufficient, complex models like decision tree regressor or random forest regressor are employed to capture nonlinear relationships. It is vital to use k-fold cross-validation to gain a robust measure of performance and to detect overfitting, a common issue where models perform perfectly on training data but poorly on unseen validation folds. Fine-tuning hyperparameters. Systematic optimization is achieved using grid search CV or randomized search CV. These tools explore combinations of hyperparameters, such as cluster counts or feature inclusion limits, using cross-validation to identify the best model configuration. Randomized search CV is often preferred for large search spaces because it samples combinations effectively, saving computational time. Ensemble strategies. Performance can often be boosted by combining models, known as an ensemble. These systems often outperform individual models by averaging predictions or leveraging the complementary strengths of different algorithms. Analysis of feature importance further assists in refining the model by identifying the most influential predictors, allowing for feature selection and the removal of noise. 3. Deployment, monitoring, and maintenance. System deployment. Once a model is finalized and evaluated against the test set, it must be prepared for production. Saving the model with job labellos for easy transfer to production environments. Whether deployed as a dedicated web service via a REST API or through cloud platforms like Google Vertex AI, the objective is to make the model accessible for real-time predictions while maintaining the ability to scale. Monitoring for model decay. Production systems require constant oversight. Model rot occurs when the data shifts over time, leading to performance degradation. Monitoring live performance through downstream business metrics or human-in-the-loop evaluation is essential. An automated pipeline that collects fresh data and retrains the model on a schedule helps keep the system accurate and resilient to shifting environmental conditions. Operational infrastructure. Robust MLOps practices involve keeping backups of both models and datasets. This allows for quick rollbacks if an updated model performs poorly or if the fresh data stream is corrupted. Automating the evaluation of new versions against the previous iteration ensures that deployments improve the system rather than hinder it, transforming the development cycle from a static experiment into a sustainable production-grade infrastructure. Summary. The provided content details the essential stages of a machine learning project, from initial problem framing to the complexities of production-grade deployment. Through the lens of the California housing prices dataset, it highlights the importance of rigorous data preparation, including handling missing values, feature scaling, and utilizing custom transformers within Scikit-Learn pipelines. The narrative emphasizes the right algorithm is crucial. The ultimate success of an end-to-end system lies in effective validation strategies like k-fold cross-validation, meticulous hyperparameter tuning via grid or randomized searches, and the implementation of ongoing monitoring processes. Ultimately, building a reliable machine learning system is an iterative, infrastructure-heavy process that demands both technical proficiency and a deep understanding of data quality to ensure that predictions remain accurate and valuable over time.
That's great. So you can see this. The summary is so great. Okay. Going to make a podcast of this quick podcast, a thoughtful talk, and English India. I'm going to uh, discuss chapter 2. Okay, fine. That is great. Okay. So it's done. Now the podcast is starting. Oh, brother. That's really very great that it's starting very soon.
Many real estate companies.
1 minute. I think the audio is off now.
Many real estate companies.
I think you can see. Yeah.
Many real estate companies
Let me refresh it. Fine.
many real estate companies
Network issue is
grapple with
there.
a seemingly straightforward
1 minute. What I will do? I'll just go back and then just click it.
many real estate companies grapple with a seemingly straightforward many real estate companies grapple with a seemingly straightforward
Question: how to accurately price homes? There's very issue with the server. Server is issuing. Okay, it's okay. Don't worry about it. So starting my this course, opening Unity. Okay, finally I have opened it after so many days. So starting from this basic 2D game, I think if I first have to log in. Okay, log in here, sign in, and sign in here too, and check it out. Is working or not working?
many real estate companies grapple with a seemingly straightforward question: how to accurately price homes.
Network issue is a lot of that. It might just become very totally what's it? Really very challenging to me. So going to start. Okay,
So, right from the
from
outset, the
from here,
book
from here.
emphasizes working with real world data, which makes sense. What is the very first step in framing a problem like? So, right from the outset, the book emphasizes
This is again an issue. Okay.
many real estate companies grapple with a seemingly straightforward question: how to accurately price homes. But what if their existing manual methods are consistently off by over 30%? Today, we are exploring the journey of tackling such a complex business problem, transforming it into a machine learning solution, and building it from start to finish. Noah, this sounds like a familiar scenario for many data scientists. So, right from the outset, the book emphasizes working
Yeah,
with
yeah,
real
yeah.
world data, which makes sense. What is the very first step in framing a problem like this?
The first step is always to understand the business objective. We are building a model to predict median housing prices in various districts. This output is not an end in itself. It feeds into a larger machine learning system that decides whether an area is a worthwhile investment. Knowing this context shapes every subsequent decision. It provides a crucial baseline. The fact that human experts are off by over 30% tells us two things. First, there is significant room for improvement, and second, we cannot expect perfection. It also guides our choice of machine learning task, given that we are predicting a continuous numeric value, the median housing price. This is clearly a supervised learning regression problem.
And is it univariate or multivariate regression?
It is a multiple regression problem because we are using several features like population and median income. However, it is univariate regression as we are only predicting a single value, the median house price. As for learning type, since there is no continuous data flow and data fits in memory, batch learning is suitable.
What about the performance metric? RMSE is mentioned as typical. Why that over, say, mean absolute error?
The root mean square error, or RMSE, is a common step is always to understand the business objective. We are building a model to predict median housing prices in various districts. This output is not an end in itself. It feeds into a larger machine learning system that decides whether an area is a worthwhile investment. Knowing this context shapes every subsequent decision.
It provides a crucial baseline. The fact that human experts are off by over 30% tells us two things. First, there is significant room for improvement, and second, we cannot expect perfection. It also guides our choice of machine learning task. Given that we are predicting a continuous numeric value, the median housing price, this is clearly a supervised learning regression problem.
And is it univariate or multivariate regression?
It is a multiple regression problem because we are using several features like population and median income. However, it is univariate regression as we are only predicting a single value, the median house price. As for learning type, since there is no continuous data flow and data fits in memory, batch learning is suitable.
What about the performance metric? RMSE is mentioned as typical. Why that over, say, mean absolute error?
The root mean square error, or RMSE, is a common choice because it penalizes larger.
Again, the issue is there. I think I have to. Network issue is there. A lot of network issue. The network is not proper working.
Why that over, say, mean absolute error?
The root mean square error, or RMSE.
Again, the same issue. What I will do, I will uh, start this podcast after some time. Okay. So thank you so much for watching it. Now I think I have to stop here. Okay. Thank you so much. Going to end this video. Goodbye. Good night.